Section 2.3 is characterizations of invertible matrices. So characterizations are equivalences, is another way to sort of rephrase that. And what I mean by that is A being an invertible matrix is equivalent to a lot of other statements that we could make. So this section is essentially one main theorem, and that's this invertible matrix theorem. And it gives us this whole long list of equivalences about A being an invertible matrix. So if A is an n by n matrix or a square matrix, then all A through L of these statements are equivalent. So any one of these things are logically interchangeable. So that's a really nice, interesting set of facts. A lot of these are really just sort of a recap of things that we've already made connections to. And the book does a decent job of mapping through all the logic of each of these, of whichever one of these statements implies another one. I believe part of the logic is that A implies J is one of the first things they do, and then J implies D, and then D, I think, implies C, and they continue through this whole chain of implications until they've completed this full loop, and we have equivalences for everything. Remember that if you prove all these implications in terms of a loop, well, then we can we know that we have equivalences, because if A implies B and B implies C and then C implies A, then we know that B also implies A by traveling the loop. That said, I don't think it's prudent to spend a whole lot of time in a video digging through all the little details of this proof, because a lot of those have already been done. And this is essentially just a recap list of all the different equivalent statements. So some of this looks more or less familiar. So A is row equivalent to the n by n identity matrix. So that's a cool trick to know now, something that we probably already suspected or have seen. If we can make A row equivalent to the identity matrix, the n by n identity matrix in its space, then we know that it will be invertible. And that's, in part, we've known that because if that's the case, it has n pivot positions. Right, so that brings us down to this next one. If it has n pivot positions, then it has no free variables, and it has no free variables, then it has only the trivial solution to the homogeneous equation, right? And this sounds like it's a chain of conditionals that are implying things, but they're actually, of course, they're equivalent. But I'm just traveling through one direction of those implications potentially. And if it has only the trivial solution to this, well, then now I'm tempted to go backwards, right? Then it's going to have linearly independent columns and so forth. So we could see that all of these things intuitively, we expected them to be kind of compiled together in a list like this, the actual proofs of which could be sought out in your own time. So another one is that the transformation T of X with A as its standard matrix must be 1-to-1. That makes sense in terms of invertibility, because if we map from one space to the other and we're not 1-to-1, say something like this has happened, then how do we go back? What does this point map back to? We want to think about that in terms of inverses, right, or mappings. If our mapping T or A was not 1-to-1, then we don't have a well-defined function that goes in the other direction. And that's exactly what an inverse does anyway. So that's more or less to have been expected. Let's see, the equation AX equals B has at least one solution for each B and Rn. Yep, okay. It has at least one solution. It should also have exactly one solution, right? Because, well, it's 1-to-1 as well, right? It shouldn't have more than one. So anyway, for a given B. Now the columns of A span Rn, right? That's also an expected scenario. So really this is just all the usual suspects rounded up into one theorem. So depending on what your application might be, any one of these things could be useful. So maps Rn onto Rn, that's great to know. There exists a matrix C such that C times A is the identity. Similarly, a matrix D such that A times D is the identity. This looks a lot like the inverse relationship, and that's essentially because it is. and then A transpose is an invertible matrix. So namely, we saw in the last section that A transpose is invertible, and A transpose, the inverse of it, was just the transpose of A inverse. So we saw that in the last section. Anyway, it's a nice list here of results, and if you're stuck with two things that feel like they might not be very well connected, and you're trying to solve a problem or answer a question, and there's about an invertible matrix, then there's a good chance you might find an equivalence on this list that'll help you out. So let's have a look at a corollary result first, right? So if we have two square matrices A and B, and if it happens that A times B is equal to the identity matrix, then we can conclude that A and B are both invertible, with B equal to A inverse and A equal to B inverse. Well, how does this corollary come about? Well, let's think about it this way. For A, there's a matrix who, when we multiply it on the right side of A, we get the identity. Well, let's go back to the previous page. We have a matrix A, we multiply it on the right. We have a matrix A, multiply on the right by something else and get the identity. This is equivalent to A being invertible. We could do the same thing for B, considering B is our n by n matrix, and we have B, we multiply it on the left by another matrix on the other page, that's A over here, right? We get the identity, and that means that this matrix B is also invertible, right, for similar reasons. So A and B are invertible, so that falls right out of this equivalence theorem that we've got right here, the invertible matrix theorem. And then its inverses are B equals A inverse and A equals B inverse. Now, of course, we would have guessed that, but how could we prove that to be very thorough about it? Well, we note this. If we have A times B equals I, well, that's equivalent to the same equation if we multiply by A inverse on both sides. AB equals A inverse times the identity matrix. Well, on the right-hand side, that's just A inverse because the identity matrix is not going to change A inverse. And on the left-hand side, we can group A inverse and A to cancel to I, and we have just a B, and that's equal to A inverse. So we get one of those statements. To get the other one, you multiply both sides by B inverse on the right of these expressions, and you get that B or A is equal to B inverse. So that's a quick hop to get to this corollary or extra results. So now let's use it in a much more practical setting. We're given a matrix, this 3 by 3 matrix here, A, and we're asked to determine whether or not it's invertible. So rather than going about trying to invert the matrix, we could take our maybe the fastest path possible towards that. And if we look back at our equivalences, what sorts of things can we do to A in order to figure out whether or not it's invertible? So it being invertible, well, it's row equivalent to the n by n identity matrix. So we could seek out its reduced row echelon form. If we get the identity matrix, then we know that A is invertible. That might be more work than we want to do because it looks like we could just stop here. If A has in pivot positions, then A is invertible. So let's aim for that. It's less work to get to just pivot positions versus total reduced echelon form. So let's see how we do. So let's put A into echelon form and observe the number of pivot positions. So again, once again, we're just going right back to putting something into echelon form. It's the key skill in the course, and really most of anything else so far has just been interpreting what it means in the current context. So I've already got a leading one, first row, first column. I'm happy with that. I'm going to zero out everything below it. So first column or first row is going to stay fixed. Second row is itself minus 3 times row 1. So I have a 0 here. 1 minus 0 is 1. -2 plus 6 is 4. Then I have 5 times row 1 added to row 3. So this zeroes out. I have -1, and -10 and 9 is -1. Let's add row 2 to row 3. So I already have a leading 1 right here. That works out just right. Let's zero out below that. I have 1, 0, -2. And then I'll have 0, 1, 4. And then this will be 0, 0. 4 and -3 is 3. And I could change that 3 to a 1, but we're in echelon form, so I'll pause right here. It's the quickest way to get to an answer. We have a pivot position in every row. And by that alone, we now know that this matrix is invertible thanks to that. And that's thanks to the previous page. If we look back again, we have a pivot, we have in pivot position. So sorry, that's in an n by n matrix, that translates to a pivot position in every row for an n by n matrix because we have n rows. So in pivot positions, 1 in each row, we're all set. So since A has 3 pivot positions, so in other words, no free variables is the other thing to keep in mind. 3 pivot positions. It is invertible. Remember, A was a 3 by 3. If it has 3 pivot positions, it's invertible. If it's a 4 by 4 with 4 pivot positions, it's also invertible, so on. So maybe why is that the case? Well, remember that in order for it to be invertible, it should not have a non-trivial solution to the homogeneous equation, right? So we put a column of zeros there. The only solution this has is that is the trivial solution, that x3 is 0, and then that translates, that's going to make this line force x2 to be 0, and then with those x2 and x3 being 0, it's going to force x1 to be 0. Right? And when we have a trivial, nothing but non-trivial solution to the homogeneous equation, we've got an invertible matrix A. And that's the other way to think about it is if we put A and augmented with the matrix I, then we could eventually, if we put this to reduced row echelon form, get the identity matrix, and then adjacent to it, all the elementary row transformations we would have done over here would give us the A inverse matrix. So if we're not looking for the inverse directly, then all we're going to do is deal with A on its own and see whether or not we get full pivot positions or if we can get it into reduced echelon form that matches the identity matrix or whatever n by n size matrix we're dealing with. There we go. Lots of different ways we could have answered this, and I think we picked the fastest one we could come up with to get there. So that's nice. So let's put this more in the context of or let's talk about linear transformations that are invertible. So a linear transformation from Rn to Rn is said to be invertible if there exists a function S from Rn to Rn, and we're really thinking about going backwards from the codomain to the domain, even though they're the same sets, both are real space dimension n, and these two conditions are met. So S of t of x gives us back x, and t of s of x also gives us back x. Remember back to functions of a real variable or a single variable. We in calculus, we talked about f of f inverse of x being x and f inverse of f of x getting back exactly what we plug in, right? Maybe something, I guess, related to that would be the function f of x equals x squared, and we're only dealing with x values that are positive, 0 to positive infinity. That way we can properly include square root of x as our inverse function to that x squared function, and we find that, yeah, these are inverse. It's an invertible transformation because we're only using the right half of the parabola, and we have an inverse function for it right here. Now that is exactly what we're doing when we generalize this concept here to S and T. So S is actually acting as T inverse, and we'll write it as that once such a mapping exists. So we have a theorem about that below. And this really, the proof of this is just a matter of writing down all the notation. Right? There's not much more to it once we define what an invertible transformation T is and give it some notation. The rest of this just falls into place by finishing out what that notation implies. So if T is a linear transformation from Rn to Rn, and A is its standard matrix, then T is invertible if and only if A is invertible, as an invertible matrix. And in this case, the transformation S of X, or the inverse transformation of T, is A inverse X. That is not at all a surprise, because think about it like this. If we write down T of X, well, if it has standard matrix A, then the transformation T is just matrix multiplication of A times X. Now say this is equal to some image vector Y. Now suppose we take Y and we want to recover X from it. Well, the way we get to that is A inverse against Y, because that's A inverse against A X. And on this side we have X. So we're going backwards from Y to X through the inverse A. And so we have this statement here, A inverse Y is equal to X. So the inverse function of T is just given by the, or it has standard matrix A inverse. And that's the quick and easy way to get to inverses for transformations, for linear transformations, provided that its standard matrix is invertible. Now, if there was no such matrix, then of course the transformation itself couldn't be invertible either, right? Because if A was not invertible, but somehow we were going to suppose that T is invertible, then we're going to realize that there's a case where this does not hold, while this does. And well, this would have to work for T inverse, and we would see that we get a contradiction arriving from that. But again, the proof of that is not necessarily that difficult, but just noting that we access the inverses of linear transformations through their standard matrix, and it tells us whether or not those exist, and it actually tells us what it is if it does exist. So there should be no surprises about that. Now, this is just one question that kind of just tests our connection of transformations to our standard matrix. Since we just talked about it, it's not really a very surprising question, but this theorem connecting inverses of transformations, and then this theorem about to their standard matrices, and then this theorem about invertible matrices really are the two combinations you'll use for any questions about linear transformation and whether or not it's invertible, or if some property tells us something else. The quick answer to this question, by the way, before I read through and talk about some more details in it, just for the learning involved there, the quick answer to this is this: what conclusions can be drawn about a linear transformation from T from Rn onto Rn? Well, if T is a linear transformation, then it has a matrix representation or standard matrix A. And if T is onto Rn, A is onto Rn as well. If we go back to our original theorem in this section, we realize that A is onto, and here we see that A of X being onto Rn, or A times X being onto Rn, tells us that A is an invertible matrix. If A is an invertible matrix, then T has an inverse, namely A inverse. So we know that our linear transformation T is invertible. There we go. That's the short answer to this. Now, maybe we want to think a little bit more about it. It's always worthwhile. This is not a necessary way to answer this question, but it gives us a little bit more information and a little bit better connection as to why this might be true. So again, T is linear, so it has standard matrix A, we'll say, which is an n by n matrix because we're going from Rn to Rn. T is onto Rn means for every B in Rn, there exists an X such that Tx equals B, or in other words, the equation T of X equals B has a solution. Okay, or equivalently, A times X equals B has a solution. So if A times X equals B has a solution for every value B we could possibly come across, then A has a pivot position in every row of its echelon form. This is from the equivalence theorem of section 1.4. Yet again, we use that result all the time. So if this has a solution for every B, then A has a pivot position in every row of its echelon form. So in other words, if A is onto, then A has a pivot position in every row of its echelon form. This means that A is row equivalent to the identity matrix. In other words, if we carry that out further, we'll have pivot position in every row. There are n rows, so there will be n pivot positions. If there are n pivot positions, when we go to reduced echelon form, A is going to be the identity matrix. Exactly, right? Its reduced form will be the identity matrix. So that's row equivalent to the identity matrix. So that being the case, we can reduce A to the identity matrix. And if we remember back to section 2.2, it's quite nearly the definition of A being invertible. So all those elementary row operations, now this one's a characterization, all those elementary row operations that we perform on A to reduce it to I, remember if we perform those on I, it builds the inverse A inverse for this matrix A. Then A inverse stands in place as the inverse of our transformation T. So we really took maybe a circuitous route to get there in this, but it touched on a few more results that we've worked in this class. It got a little bit more into the details. And if you can roughly follow the argument of this, then you're doing well. But otherwise, just keep in mind that if you just go to the equivalence theorem or the invertible matrix theorem in this section, you can answer this question as simply as that in the way that I initially did. But being able to sort of freely move through this logical space regarding matrices and their inverses and one-to-one and onto it makes you that much more powerful with this material and be that much more successful in the course. So that's it for 2.3. We'll begin chapter 3 in the next video, where we'll start talking about determinants and how to use determinants to calculate potentially inverses or determine whether or not an inverse for a matrix might exist.